Our next topic in ECE 111 is ECE 320, Electronics 1. Now, in electronics, we cover the analysis of circuits made with semiconductor devices. These include thermistors, which are temperature sensors, diodes, which act as valves, allowing current to flow in only one direction, transistors, which are a combination of a diode plus a current amplifier, semiconductor relays, which are voltage-controlled valves, and MOSFETs. MOSFETs are voltage-controlled resistors. Now, the challenge in ECE 321 Electronics 1 is the devices we're looking at are nonlinear. So when you have circuits with diodes, transistors, SCRs, and MOSFETs, you're trying to solve a set of n equations for n unknowns where the equations are nonlinear. That's the challenge of electronics. Now, a little bit of background. In electronics, we deal with devices made out of semiconductors. Semiconductors are silicon and germanium primarily. They're in column 4 of the periodic chart. What that means is that if you have a crystal made up of pure silicon, each silicon atom has 4 neighbors. All the electrons in the outer shell form covalent bonds with their neighbors, meaning that there are no free electrons to carry current. If you raise the temperature above 0 degrees Kelvin, a few of the electrons will gain enough energy to jump out of their covalent bond. At that point, that electron has no place to go. All the other covalent bonds are filled, so the electron is free to roam throughout the crystal. That carries charge. There's a second type of way to carry charge. The missing electron in the covalent bond is called a hole. That looks like a plus charge. A neighboring electron can jump out of its covalent bond and fill the hole, making it look like the hole's moving. So for semiconductors, they're a little bit different than metals. For semiconductors, I have 2 ways to carry charge. I've got electrons and holes, which looks like a negative charge and a plus charge. Now, when I dope semiconductor, I can control how many holes and how many electrons are in it. If I dope the silicon with boron, what happens is boron is in column 3 of the periodic chart. It only has 3 electrons in its outer shell. That 4th covalent bond doesn't have an electron. That creates a hole. When you dope silicon with boron, you wind up with primarily holes as the charge carriers. Conversely, if I dope with phosphorus, phosphorus is in column 5 of the periodic chart. It has 5 electrons in its outer shell. 4 of the electrons fill the covalent bonds. That 5th electron has no place to go, so it's free to roam throughout the crystal. That creates what we call N-type silicon, where almost all the charge carriers are electrons rather than holes. By doping the silicon, I can create N-type material and P-type material. When I put those together, I get different devices. For example, a PN junction is a diode. It's a valve that only allows current to flow one way. NPN is a transistor. That's a combination of a diode plus a current amplifier. PNPN is a semiconductor relay, or SCR. This is a diode that you can turn on and off. There's also other devices like a MOSFET, which is a voltage-controlled resistor. In electronics, we cover various devices made with semiconductors, meaning made with PN junctions. Today, we'd like to look at just one of these, how to analyze a circuit that contains diodes. Now, a diode is a nonlinear circuit element that acts like a valve. When I apply current, or try to push current flow from the anode to the cathode, the resistance is very low. When I try to push current backwards from cathode to anode, the resistance is very, very high. Hence, the symbol for diode is an arrow reminding you current flows anode to cathode. The characteristics for a diode are highly nonlinear. A typical diode is in this form, where the current is an exponential function of voltage. So for a silicon diode, you'd have typically this type of VA characteristic. As the voltage increases, the current doesn't go up linearly, it's exponential. The challenge with diode circuits is how to analyze a circuit where you have nonlinear elements. Take, for example, one of the simplest cases, a simple single resistor, single diode, and 10-volt source. To write the equations, I wind up with 2 equations, 2 unknowns. My 2 unknowns are the current through the diode and the voltage across the diode. One of the equations is just the diode equation. The second equation comes from the circuit, and that would just be the voltage across the diode Vd plus 100 ID must equal 10. With two equations, two unknowns, in theory, you can now solve. One way to solve these, since they're nonlinear, is called load line analysis. What I do is I draw the VI characteristics for a diode, that was my first equation, draw the second equation, that is 10 volts is Vd plus 100 ID, that gives you a straight line, called the load line. The intersection is the solution. And so in this case, the solution is right around 0.9 volts at about 90 milliamps. I can also do a numerical solution. In MATLAB, I can sit there and guess the voltage. If I guess the voltage, what I want is what voltage makes these two curves match up. So in MATLAB, what I do is I guess the voltage, calculate the current, and then the error is, ideally, is 0. The current that satisfies the diode equation also satisfies the load line. The error is the difference in the two. If I return the sum squared error, I can now come up with a function where I guess the voltage and I want to minimize the sum squared error. The MATLAB function fininsearch can do that. With fininsearch, I can now find the actual voltage and current through the diode. Second example, suppose I have multiple diodes. In this case, there is a solution. If I built the circuit, I would have some voltage at V1, V2, V3. Those voltages are whatever it takes to balance. Whatever voltage it takes so that the current in equals current out. In this case, a numerical solution or load lines won't work. If I had a load line, I've got 6 equations, 6 unknowns. That's difficult to plot on paper. A numerical solution will work, however. To do that, what you do is set up your 6 equations, 6 unknowns. 3 of the equations are just the diode equations. The current through the diode is a function of the voltage across the diode. For the first diode, the voltage is V1 minus V2, so that goes in for Vd. The second diode, the voltage is V2 minus V3. The third diode, the voltage is V3 minus 0. That gives you your currents through the diodes. That's 3 of your 6 equations. The other 3 equations are just the voltage node equations. At node 1, the current left, down, 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 as to 0. That's this first equation. At node 2, the current up plus the current down plus the current right equals 0. And note that I'm just using ID1, ID2, ID3 for my currents through the diodes. The previous 3 equations already define those. And likewise for node 3, I now have 6 equations, 6 unknowns. Solve. This is where fininsearch is nice. What I'll do is I'll guess V1, V2, V3. Given those voltages, solve for the currents through the diodes. From the voltage node equations, if I guessed correctly, the current should balance. If I guessed incorrectly, they won't balance. I'll have a non-zero E1, E2, E3. I'll now then compute the cost, is the sum squared error, and use fininsearch to minimize the cost. To do that, I'll create a function in MATLAB called cost, completely original name. I'm going to pass z. MATLAB is a matrix language. It wants to pass a matrix. What z means is that's my guess in the voltages, V1, V2, V3. Once I know the voltages, calculate the currents through the diodes, calculate the excess current at each node, and return the sum squared of the excess currents. With fininsearch, I can now tell MATLAB to say, here's my cost function, here's my initial guess on voltages. What voltages minimize the sum squared error? fininsearch will then guess again until it comes up with an answer. And it says the answer is 2.9, 1.9, 0.9. The sum squared error is almost 0, meaning it did find the answer. So with fininsearch, I can actually solve diode equations. When you do things like input a circuit into CircuitLab and tell it to solve, that's actually what CircuitLab's doing. It's trying to iterate, trying to figure out what voltages make the currents balance. Once it finds the answer, it will display the results. That's some of the things we do in Electronics 1. In terms of MATLAB, given a circuit with nonlinear elements, I can solve, just like we do with linear elements, except that now I need to use fininsearch.